Okay, so today we're really diving deep, get ready for it, into deep generative models.
DGMs for sure.
Yeah, DGMs for short, exactly. And I know that might sound a little intimidating, like something straight out of science fiction.
Yeah, it kind of
But
does.
I promise it's not as complicated as it sounds.
Yeah.
These are actually already being used in transportation research
Yeah.
and having a real impact. Like, imagine a world, and I think a lot of people listening can, where you can test out a self-driving car in a simulated blizzard
Yeah.
or predict traffic jams before they even happen. That's the kind of power we're talking about here with DGMs.
And that's what's really exciting about these models. It's not like your traditional AI where it's just analyzing data. We're talking about AI that can learn from existing information and actually generate new data points. So it's like having this, like an AI imagination almost.
So instead of just looking at past traffic patterns, it can kind of envision what might happen. And that's huge, right? Because like you said, transportation, it's not just about what has happened, it's about preparing for what could happen.
Exactly. And especially, like you were saying, transportation, when you have things like accidents or even just sudden weather changes, that can really throw a wrench in everything.
Totally unpredictable, so if we could get ahead of that. So it's like having, I don't know, like a crystal ball, but for traffic.
Yeah.
It can see those congestion hotspots before they even form.
Yeah. And not just like a single prediction. You're going to have like a range of possibilities, and then you can assign probabilities to those.
Oh, wow.
So, kind of like how you see with a weather forecast. Instead of just saying expect delays, it might say, well, there's a 70% chance of heavy congestion, 20% chance of moderate, and, a 10% chance it'll be smooth sailing.
And that's useful for, well, obviously for someone like me driving around, but also for people who are actually managing these systems.
Absolutely. But the challenge is really when you're building these models, you're trying to balance a lot of different things.
Hmm.
Like on the one hand, you want your model to produce really high quality data.
Mm.
Like if you think about it like a photograph, you want something that's like super crisp, super realistic. But you also want it to capture the full diversity of what you see in the real world.
Like a dynamic, bustling city.
Exactly.
Yeah.
So it's kind of like you want that single perfect snapshot, but you also want to capture the energy of, an entire city.
And do it quickly, right? Because, I mean,
And do it quickly, yeah.
the real world doesn't wait, so there's no pressure on these DGMs.
Right. And that's why researchers are always developing these new types of DGMs, and they all kind of have their own strengths and weaknesses.
Okay, let's break down some of these different types then. So first up, we've got VAEs, Variational Autoencoders. Is that right?
Yeah. And you can kind of think of those like, those AI image generators you might have seen online.
Mm.
They're really good at capturing a wide range of styles and features, but the results can sometimes be a bit blurry, if that makes sense.
Okay, so good for diversity, but maybe not always, ultra high definition.
Yeah, exactly.
Okay, what about GANs then? These generative adversarial networks, I feel like I hear those thrown around a lot.
Yeah, and GANs are kind of like the masters of realism when it comes to DGMs.
Yeah.
They can create these super detailed, very convincing data points. But the trade-off there is sometimes they can get a little stuck, like an artist who can only paint one thing. And we call that mode collapse.
Mode collapse, it's like that friend who makes a mean omelet,
Exactly.
but ask them to make anything else and they're completely lost.
And then you've got normalizing flows,
Mm.
which are really about speed and precision. So like a well-oiled machine, but they might not always achieve the same level of realism as those GANs that we were just talking about.
Yo, efficiency is their game.
Exactly.
Okay.
And then kind of rounding things out, you've got your diffusion models. So you can think of those like, imagine an artist who starts with a blurry sketch,
Okay.
and then they kind of gradually refine it until they have this really beautiful masterpiece. So they're all about that balance between quality and diversity.
Okay.
And then finally, you've got your score-based models. And those are very similar to diffusion models, but they're really known for their ability to capture those really fine-grained details.
So if GANs are like those big, broad strokes,
Exactly.
these are going in with like a tiny, tiny brush, getting every single detail.
Exactly. It's like a hyper-realistic portrait.
Oh, that's really cool. This is already blowing my mind, and we're just getting started. But before we get ahead of ourselves, let's talk about how this is actually being used, because I'm already picturing self-driving cars. I'm picturing smarter traffic lights. Like, this has got to be applicable to so many different things. We talk about self-driving cars, we talk about these smart cities, and one thing that always comes up is data.
Yeah.
We need tons of it.
You need data for anything you're doing, especially in transportation, if you're going to be training AI systems.
Right, because you need to train them on every single possible scenario.
And the problem is, getting that real-world data is really hard.
Oh, I bet.
It's expensive, it's time-consuming, and sometimes it's just impossible, right? You can't just go out and cause a snowstorm on the freeway to see how your car's going to react.
No, definitely not. Please don't try that at home, listeners. Or anywhere else.
Yeah, you'd be waiting a really long time to get enough data to actually train your system.
Right.
So that's where these DGMs come in. Instead of waiting for the real world to kind of give you that data you need, you can generate it.
So we're talking about like AI-generated traffic jams, basically.
Yeah. Yeah, you can create these synthetic data sets that you can then use as testing grounds.
Oh, cool.
So imagine like being able to test out, a new traffic light algorithm or a self-driving car strategy. But you can do it all in this kind of safe, simulated environment.
So it's like a digital sandbox for these urban planners, where they can test out their wildest ideas, break things, and it doesn't matter. No
Yeah.
real-world consequences.
Exactly.
That's amazing. Okay, but like, is this actually working? Are there examples of this being used in the real world?
Yeah, there are. So there was this one study where they used DGMs to actually create synthetic traffic volume data. And they found that they could improve the accuracy of traffic flow predictions
Yeah.
using this synthetic data,
Wow.
which is pretty amazing.
Yeah, that's huge. So we're talking about generating data, making predictions, but what about understanding the data that we already have?
Yeah, so DGMs can also do something pretty cool called unsupervised representation learning,
Okay.
which sounds complicated, but bear with me. Basically, you take all of this raw traffic data you have. You've got like speeds, GPS locations, you name it. And a DGM can sift through all of that without any labels or instructions and start to identify patterns.
So it's teaching itself.
Yeah, it's like teaching itself.
It's teaching itself to read traffic.
Yeah.
Like it's its own language.
That's a great way to put it. It's kind of like, when you teach a kid to recognize animals, but you don't tell them what the animals are.
Right.
They start to see the similarities and differences.
And they figure it out.
Exactly.
Oh, that's cool. So then instead of just seeing like a jumble of numbers and data points, it's actually understanding the nuances of traffic flow.
Exactly.
Okay.
So you can imagine a DGM that could, let's say, analyze all these different traffic patterns and identify, okay, this is what a cautious driver looks like. This is a speed demon. This person slams on their brakes all the time.
Oh, or what about like if there is a fender bender about to happen, it can spot that.
Exactly. Yeah. And again, this is not just theoretical. There was a study where DGMs were able to actually classify different modes of transportation cars, buses, bikes, just from their movement patterns in raw data.
Wow. No labels.
No labels.
That's incredible. So, I mean, we're talking about data generation, we're talking about prediction, and now this ability to like find these hidden patterns, it really seems like these DGMs could totally change how we understand and manage transportation.
Yeah, they could. And to kind of illustrate that, let's get into some more specific examples of how researchers are actually putting these models to work.
All right, so let's get into the nitty-gritty. How are researchers actually using these DGMs to like solve real-world transportation problems?
Okay, so one area where this is really taking off is in understanding travel behavior. Those travel surveys, they ask you how you get to work every day, what kind of transportation you use.
Yeah, those things. I always feel like I should just write like teleportation or something. It seems so much easier than actually filling it out.
Right. And not everyone's got time for that. But that data is actually really important for city planners.
Makes sense. Yeah.
Because if you're trying to design an efficient system, like you need to know how people are moving around.
Yeah. How do DGMs fit into all this?
So imagine if you could take those surveys, right? The ones that are maybe incomplete or have some gaps, and you could train a DGM to fill in those blanks.
Oh, interesting.
That's exactly what some researchers did. They used data from the Household Travel Survey in Seoul, South Korea.
Mm.
And they wanted to see, okay, can we train a DGM on real data and then have it generate synthetic data that's just as good or maybe even better?
So you're creating like these little virtual commuters almost. with their own travel habits.
Exactly. Yeah.
Yeah.
And they looked at like, where trips started and ended, the reason for the trip, what mode of transportation people were using.
I bet that last part, the mode of transportation, that's tricky, right? Because it's not like you're dealing with like a speed or distance. It's a category, right? It's a bus or a train.
Yeah, you're totally right. With this kind of data, it's categorical. It's not like drawing a smooth line.
Yeah.
It's more like jumping between different, like stepping stones.
Okay.
So to get around that, they use this technique called dequantization. That's a mouthful.
Dequantization. Okay.
But essentially what it does is it kind of smooths out those boundaries between those categories. So instead of those sharp jumps, it's like you're walking on a ramp now.
Oh, okay. So it just makes it easier for the DGM to navigate between those options.
Exactly.
Did they just stick with one type of DGM for this, or did they try a bunch?
No, they actually tested out, the VAEs, the GANs, the normalizing flows. And what they found was each one, just like we were talking about earlier, they all have their strengths and weaknesses. So, for example, VAEs, they were pretty good at capturing those overall patterns, but sometimes they struggled with those really specific details.
Like if someone was more likely to take the bus versus the train.
Exactly.
Gotcha.
And then the GANs, they love realism.
Right.
Sometimes they get stuck in a rut. They would generate like the same few travel patterns over and over again.
Okay, so it's really about picking the right DGM for the job. There's no one size fits all.
Totally. And that actually leads us perfectly into the second example.
Hmm.
This time we're zooming out. We're looking at highway traffic flow, big picture stuff.
Okay, so instead of individual commuters, we're looking at the whole system.
Exactly.
Yeah.
So imagine looking at a live traffic map.
Yeah.
But instead of just seeing, red and green lines, you see how that traffic is flowing over time, like a heat map that's constantly changing.
Oh, cool.
And these are called time, space, speed contours.
Okay.
And they're really helpful for understanding, like how traffic is actually moving, where those bottlenecks might be. But you need a ton of data to create these.
Yeah, way more than just a couple of traffic cameras.
Yeah, way more. But in this case, these researchers had access to a really cool data set from the Tennessee Department of Transportation. They've got this project called I-24 Motion, where they're actually using these high-tech cameras to track every single vehicle along a stretch of highway.
So no more of those like sensors in the road. It's like cameras from above.
Exactly. It gives you this incredibly detailed view of what's actually happening out there.
Yeah.
But even with that, they still had to do some cleanup.
Oh, really? Even with this amazing data?
Oh, yeah, because you're always going to have glitches. Sometimes the cameras would miss a vehicle, or there would be like, weird stuff in the data.
So it's like polishing the diamond before you can really appreciate it.
Exactly. They had to use some interpolation to fill in those gaps. And they actually applied something called, it's a mouthful, Edie's definition of traffic flow dynamics.
Okay, so I'm not going to pretend to understand all the technical stuff, but what does that actually mean? What is that in a nutshell?
So essentially, it's a way to describe how traffic behaves, so like how fast congestion spreads, how quickly speed changes ripple down the highway, like the physics of traffic almost.
Fascinating. So after all that work, were they able to generate those visualizations?
They were.
Cool.
And just like before, they tested out different DGMs to see, okay, what works best.
And the winner is?
Well, there wasn't like a clear winner, which is kind of the interesting thing about DGMs, right? They're always trade-offs. But the GANs, those were really good at creating like super realistic speed contours, even with a pretty simple setup.
So that visual realism, that's their strong suit.
Totally. What are those other ones? How'd they do?
Yeah, what about like the normalizing flows and the diffusion models and score-based models? How did they handle it?
The normalizing flows were kind of a mixed bag.
Mm-hmm.
Sometimes they did a great job, other times not so much. Really showed how important it is to tune them properly.
So a little finicky, those normalizing flows.
Yeah. The diffusion and the score-based models, though, those were consistently good. They were churning out high-quality speed contours, capturing all those like subtle changes in traffic over time.
It's wild. It's like they're learning the actual language of traffic.
Yeah, kind of.
But I'm guessing there are still challenges, right? Like what are some of the things that researchers are still grappling with?
One of the biggest ones is bias. Because if the data that you use to train your DGM is biased, then the data it generates is going to be biased too.
Garbage in, garbage out.
Yeah, pretty much. Another one is explainability. So DGMs can be these really complex beasts, and it's not always clear why they make a certain prediction or decision.
Yeah, and that's kind of important, especially when you think about self-driving cars. You need to know, like, why the AI slammed on the brakes.
Right,
And
exactly.
on top of all of that, transportation itself, that's not static. It's always changing. We're building new roads. Traffic patterns change.
Right. Who knows what it will even look like in 5, 10 years.
So we need DGMs that can evolve too.
Right. It's not like you could just build one and forget about it. It's an ongoing area of research for sure.
This whole conversation has been really eye-opening. So for our listeners who are out there, and I'm guessing their minds are blown right now, what's the big takeaway?
DGMs are already changing the game when it comes to transportation. We can generate data we never could before, make predictions, find patterns we didn't even know existed. It's all about making transportation smarter, safer, and more efficient.
I'm excited for the future, and I hope our listeners are too. Thanks for joining us for this deep dive into deep generative models.